This lesson covers the topic of collinearity between predictors in a multiple regression model. Let's begin with a definition. We say two or more predictor variables exhibit collinearity when one of the predictors can be well predicted from the others. Let's step back to our home sales price example, where we fit a model to predict the sales price of a home in Saratoga Springs, New York, based on its square footage of living space and number of bedrooms. We were surprised to see a negative coefficient for bedrooms until we realized that living area and bedrooms are positively correlated. Because these two predictors are related, we can predict the living area of a home fairly well if we know the number of bedrooms. When we use both of these predictors in a model to predict home sales price, we say the model suffers from collinearity. Notice I used the word suffers, a word with negative connotation, when stating that the model has collinearity. Should we be wary of collinearity? Well, we should at least be aware of when collinearity exists and know its consequences. First, the coefficients of the predictors in the model can be surprising, being unexpectedly large or small, or taking on an unanticipated sign, as we saw with the number of bedrooms in our home sales model. Secondly, the stronger the correlation between predictors, the more the variance of their coefficients increases when both are included in the model. We call this variance inflation. The reason why this can be a problem is because it will lead to smaller test statistics, potentially increasing the p-value enough that it becomes statistically insignificant to the model. What if we consider the number of bathrooms in a home? Do you think that is an important predictor of sales price of a home? Let's start by fitting a simple linear regression of sales price on number of bathrooms. The p-value is significant for this model, and the slope tells us that this model predicts a $77,084 increase in the mean sales price for each additional bathroom in a home. Next, a simple linear regression of sales price on living area predicts an $88.30 increase in the mean sales price for each additional square foot of living space in a home. Because both living area and number of bathrooms are significant predictors of home sales price individually, let's include them both in a multiple regression of sales price. For purposes of illustrating the effects of collinearity, we will leave out the interaction term in our model. Note that the standard errors of living area and bathrooms have undergone a significant percentage increase from the simple regression to the multiple regression model. As a result, the t-statistics have decreased, which in turn increases their p-values. These changes are the impact of the collinearity between living area and bathrooms, which are clearly positively correlated. To review, when one of the predictor variables in a multiple regression can be predicted well from another predictor or combination of other predictors in the model, those predictor variables are said to be collinear. When two or more collinear predictors are included in the same model, we say there is collinearity or multicollinearity in the model. It is important to be aware of collinearity in a model because it can lead to the coefficient being poorly estimated and having a large standard error. This could lead one to conclude that a predictor is not important to the model when it actually is. Additionally, the coefficient may seem to be the wrong size or even the wrong sign. This can cause issues when investigating the relationship between a predictor and the response. To detect collinearity in a model, we use a statistic called the variance inflation factor, or VIF. The VIF quantifies the degree of collinearity of the ith predictor with the other predictors in the model. VIF is calculated by taking the reciprocal of 1 minus r sub I squared, where r sub I squared is the r squared for the regression of predictor I on all of the other predictors. A common cutoff for VIF is 4. If a predictor has a VIF greater than 4, you should suspect collinearity. Let's look at an example. Suppose we have a regression on 4 predictors named A, B, C, and D. We can calculate the VIF for each predictor to test for collinearity of that predictor with the others. Let's compute the VIF for predictor A. First, we will run a regression of A on B, C, and D. The regression of A on B, C, and D gives an R square of 90%. So to calculate VIF for A, plug in R squared into the formula. When we do this, we get a VIF of 10. Because this is greater than 4, in fact much greater than 4, we strongly suspect collinearity between A and the other predictors. Statistical software packages, including R, will report the VIF for each predictor when asked. Let's go back to our roller coasters example. Suppose we fit a multiple regression of speed on drop, length, and duration. To compute the VIFs for the predictors drop, length, and duration, we must first install a package called car. Be patient, as this may take a few moments to install. Once the cars package is installed, call the car library, and then fit the multiple regression model of speed on drop, length, and duration. Now we are ready to compute the VIFs. The function is a lowercase VIF, and the argument is the name of our regression model, which we named fit. Notice that the VIF for drop, 1.84, is lower than 4, the suggested cutoff for collinearity. So we do not have evidence of collinearity between drop and the other predictors. Similarly, we have low VIFs for length and for duration. So again, there is no evidence of collinearity. Collinearity does not affect the fit of the model or predictions using the models, but it does make choosing the best set of predictors more difficult and can also mask or change the interpretation of the effect of a predictor on the response. Suppose you have collinearity among predictors in your model and decide to remove one or more of the predictors. How do you choose which predictors to keep? Here are a few best practices on which variables to keep. Keep the variables that are most reliably measured. Keep the variables that are least expensive to find. Keep variables that are inherently important to the problem. And keep new variables that have been formed by combining variables.